So anyway, those what I talk about cannot get entertained. So I would like to give another overview on reinforcement learning. Actually, they did talk about that like a year ago, but I guess somehow I get to read some more about that, so therefore I want to talk a little bit about that. So it will be kind of overview. It's not. It shouldn't take too much time. And the more I read about this, it's kind of interesting. Like this is I study in many disciplines. Of course, I don't learning people call this reinforcement learning here. Reinforcement learning. So, and also, the control people look into that also, like as adaptive control, and they call it. Some of the people call this approximate learning programming. And also like neural dynamic programming and so on. And the operational research people also look into this one also. So therefore, like also like you often like see like people talk about this Markov dissolution process is also like basically there's very much related to this also. So anyway, like if we try to explain in the context of reinforcement learning, is that you have basically you have a machine learning system trying to learn something, and like it's not like the what's it called? I forgot. It's not like a system that like you know. It's not like supervised learning that like you know exactly what the outcome should be, and it's also not like unsupervised learning that you don't exactly what you're going to be. Like I have no idea at all, but maybe you just have like some hints like what you're supposed to do. So a pretty typical example is like driving a car and so on, like automatically. So you only know that you are going to crash or like you should move left or right, and basically the robot may be able to see like what's going on out there and just trying to determine whether it's trying to view left or right, or like whether it should press the pedal or not. And what it knows, as I just said, is like whether it crashed or not and so on, or whether it will make it to the destination. So you can model that with like this Markov decision process. So it has a decision here because you basically, it's not just like a Markov process, Markovian process that like it's just kind of like a state diagram, like you just randomly from one state to another state, but you also have a tick there, like you have an input there that you can have a basic control parameter. You can choose like what action you want to choose, and based on the action you may have different outcome. So I already mentioned this action here, and sometimes people call it control here also. So it's all depend on which discipline you are. So like the control people would like to say this is a control, and the people from operational research will call it action. And basically the system will be like that. The model will be like that. So we have some transition probability. Let's say you again like a Markovian process. You have some states here, like what kind of state you are at for the moment. So you have some state and a state set here, and let's say for different time instance, And for the next time instance, the probability, the transition probability will depend on, like, of course, your current state, but also will depend on your action, like basically the decision you made at time t. So, and then like if you are the operational research people, you will talk about reward. So based on what stage you are at, and also like what action you made, you can have different reward for kind of like instantaneous reward at this moment. And what we are interested in is not just the instantaneous reward, but most likely is a reward over the entire time period. So what we are more interested in will be something like the sum over all this time. And more precisely, you typically will add a discount factor also, because like you want to have like the satisfaction to happen earlier than later. So typically you basically just want to have something like this from, let's say, to infinity, and you kind of want to maximize this thing. It's like your total happiness discounted by this gamma here. So this gamma typically is from between 0 and 1. So then what is interesting here is like what kind of action we should do, like based on what kind of state we are at. So therefore, like people introduce a name for that as a policy. Basically, a policy is just a mapping from your state to whatever action. So let's say action here is like action set here. So your possible action is based on this action set here. So basically, whenever this is like a game plan here. So whenever you have a policy, like at each stage you know like what you're going to do. So I guess like they gave a pretty nice example last time, actually a long time ago. Let's say let's say we consider something like trying to drive a robot from somewhere to a destination. Let's say this is like your destination that you want to go. This may be something that, what should I say? I don't know. Something like anyway, somewhere that like the robot can maybe it can charge itself. It's like somewhere that therefore you want the robot to go there. And maybe there's like another place is like some trap there, like you don't want the robot to get into. And basically your robot is started at here, and then like, you move around and so on. And then like therefore like I can claim like, let's say the reward if I get there, maybe like I will say like 100 here, and if I the reward will be like minus 100 there. And for all the other cases, like, let's say it's just 0 here, whatever. And so what will be the potential action set here? The potential action set would be something like you can go either up, down, or left or right way. And maybe you can stay also, you can do anything. So you from here you may try to move up, or try to move down, or try to move left, or try to move right. And also like we can assume that because of some probability here that maybe the floor is slippery, that even though you try to go left, maybe somehow you just stuck here and didn't move, or like something like you try to go left actually like drift down or whatever. So therefore like, you have a probability here that even though you start from, let's say your state is like originally here, and you're trying to go left here, but still have a non-zero probability that you may go down, for example. So I guess the setup is quite clear here now. then basically, what we can do to find this optimal policy here. By the way, the policy typically people use pi to denote policy here. Can be can be kind of solved by dynamic programming, and you can see why it's solved. And let me just introduce one more new notation before I get into that. Let me denote something B here. It's called a value function here. So this value function, let's say, it's a function of S here, the current state here, and I can introduce several different value functions. Let's consider this first, like the value function of S, like with policy pi here. So what this means here is if I use the policy pi, I want to, this value function, you will evaluate the final the expected, actually this will be equal to the expected or actually I can just write like this. It's basically the expected total reward.
Excuse me, the value is the total reward?
Yes, it's the expected total reward. I say it's expected because remember there's some stochastic thing going on. Even though that you have all these policies basically deterministic, you say I'm stay here, I always say that you should go left, but you may drift down instead. Oh, sorry, this is white. You may drift down instead. So therefore it's like kind of like an expected value. And okay, what's this phase should be? I can actually kind of like expand this value as think of it this, like if you're at state S now, and if your action that kind of like defined by this policy is pi here. So the next, okay, so the next action should be like pi s here, right? So this is supposed to be the next action should be pi s here. And then like the reward, the instantaneous reward in the next step should be just r s a here, right? Or like this a should be pi s here. Maybe I just write pi s here. And then I will have some future reward. And the future reward will be, I may get into the state that, okay, because it's probabilistic, I have the action A, I may get into some state S pi here with some final probability S and action pi S, right? And if I get into this state, I will have what will be my future reward at that time on?
It was from the screen given the policy on the screen.
Say that again, actually, I
The
can
R of the screen and P of the screen.
Yeah, okay, yeah, it's white, but you you can see this is kind of iteratively, right? So this is the next time instant, the next.
Yeah,
the
it
same-
can be V. as
Yeah, it's basically it's like V again, right? It's like V pi S pi here, right?
Yeah.
Yeah, basically. And of course I need to incorporate this kind of factor here, so I should have a gamma here. And I can get into like all of this S pi here, so I should sum over S pi to all S here. So immediately I have an iterative equation for this V here, right? So for each policy, it's possible for me to evaluate the value of the policy and for the current state, like this. Just solve these linear equations basically. And what's more, if I define V star as this is like for a particular policy pi here. If I define V star is the value of the best policy, essentially I can write down exactly the same thing, right? It will be like in the next time step, what I'm supposed to do should be simply, let's say it can be some action that I'm supposed to do like now as A there. And let's say I take some action, I'm not going to define that yet. And it will also incorporate in the next time step, if I take that particular action, I will result in that much expected reward rate. Let's say if I take action A, so I will result in that much expected reward in the next time step. And that should also discount that by gamma again. And then of course what I should pick the A should be the A that take me to the maximum value eventually, that gives me like the maximum expected reward over the entire period. So I will just have this here.
Excuse me. This was iterative. What is the first V star?
Okay, that would be like several. One thing if you really or actually I didn't go into that yet. But if you try to just solve this equation, you don't need that, right? Because if you look at this, it's really a system of equations. Essentially, you can think of this as a this is basically just a matrix multiplied by this vector here, right? And you basically have something a form like something like C is equal to some A times V is equal to V, something like that. So we can solve this system of equation just, okay, this would be like V equal to like 1 I minus A inverse like C or something like that.
But here, the V star sphere is not the same as the V star S. Yeah, this one
So
is,
equal to this?
yeah.
No, this is the same. This is the same V star here.
No, I mean the S and S.
The S and
Yeah, this one is a V star S prime, that one is a V star S.
okay, this is some of our star here. So some of all stays here, and this is basically think of that like this is like a vector here, like different S and A here is like a vector, right? And you are multiplying this with another state is like
Okay.
vector also, yeah. So and then this is like
Okay,
corresponding
you mean
to
the
this.
BS star, just, okay,
Yes.
BS star is same, this is not, it doesn't matter. The BS star is for both sides is same, yeah, okay. Yeah,
Yeah. Like this S star is like basically a dummy variable here, like move from here to here. So let's say your S is basically 1 here. S equal to 1, the first stay here. You basically have the first S equal to 1 is the first vector you multiply this way. And then S equal to 2 have another something like this multiplied by this. So it's basically like existing equations. And this is called a Bellman equation. Actually, they mentioned that, like, Bellman did this in the 50s. Okay, so just based on an idea like this, we can divide algorithm to find your best action, or like actually I should say the best policy. So there's typically two approach I can do. Like one is call it we will call it a value iteration. So in a value iteration approach, let me just write it down first. For S here, for A here, Q S A here, S R S A, S S here. Let's start with this first. So what I show here is basically I try to estimate the fact. Okay, this thing QSA here is actually basically this thing here. So what we are trying to do is just iteratively try to first estimate this QSA. So what's QSA is basically if I am state S and if I let me just write QSA is kind of like value if current action is A as state S. So kind of like you start at state S now, and then like if you pick an action A next, and then like you take the optimal action afterward. That give you come for QSA here. Okay, actually not exactly, but it's more or less like that. So then you think of this as just, okay, I'll just basically split this optimization into these two steps here. First I try to estimate this QSA and then I try to estimate this VS here. So then ultimately, like each time I just try to estimate this value function, this one here. And of course, like, if I know the value function, then the policy is basically it's just the mass of this QSA here. That if you are at state S, you should take this action A. Because like, if this thing converges, basically QSA is already, what should I say? QSA is already the, actually, maybe it helps a little bit like, let's see if I can. Like you have stay currently is S here, and then like you have this current. This state S can take multiple actions, and this leads to many outcomes.
For each action, we are programmed to point to a different state.
Yes. Yes. But V already take care of that because V is basically it's not exactly like which state you get into, but it's like what's the values after you pick that after you are at this state. And QSA here is more or less like if I pick this. So let's say this action 1, 2, 3 here. You have a QS1, QS2, let's say something like that. So I should determine which I will just pick the action that eventually leads me to the value that is the biggest. And okay, this is kind of bad. Let me just erase this, but it's it's a hard choice to make. Yeah, okay, but we need to move the camera back and forth. I try to not quite so we can do also like policy intuition. So for policy intuition, basically, I will look into each policy. I just fix an initial policy. So let's say some initial policy. Then I'm trying to compute the policy, compute value function of I for policy I. So that's the essential is meaning that I should solve this V pi as is equal to R as A gamma. So I trying to solve this V here. Then instead of trying to find the exact V, remember like this V is kind of different from this V. This V is really the optimum V. This is like the optimum in the sense that if you pick the best policy, always you will end up with this V. When we have a V pi here, it's basically saying if we use this policy pi, we'll end up with that V. So now for each policy, we try to compute not exactly which policy. We start with an arbitrary policy, and we compute the value for that policy, and then we just try to improve the policy. So we try to improve the policy by basically S is equal to the argmax of A S A So here, of course, we make an approximation here, thinking that if we change the policy a little bit, the V is like kind of more or less the same. So we approximate if more correct, we should have a V pi here. But we have this V pi here instead. But we just keep iterating, keep iterating until if our policy converges, then we can basically determine decide that we find the solution of the best policy. So you can see, like, compare these two approaches. This tends to have a lot of iteration, probably have more number of iterations, but maybe less. The conversion time will be longer. But this one is like you have a more computational heavy iteration step. Like each time you need to solve this thing, it's basically solve this type of linear equation. But the iteration time will be the number of iterations on average will be less. The problem here is like for both these two approaches, we kind of assume that we know the system model. And this is exactly not exactly, but it may not be very helpful in practice, right? We are assuming we know like what kind of reward we should have, and also like what's the transition probability supposed to be. And okay, let me just erase this now. Yes. So what thing we can do is we can actually we don't need that really. I already regret I erased it. So one thing is quite a bit popular, but actually it's a pretty old algorithm. It's called Q-learning. It's about late 80s, like 1989 or 88 or one by Walking. So how to spell this here. And for Q-learning, why you call Q-learning? So you know that it's basically the term related to this Q here. So what Q-learning is supposed to do, the idea is kind of simple. Like instead of trying to use this P and R here, we just try to approximate this Q directly. If we can estimate this Q directly, we see like we don't actually need to don't actually need to compute the we don't actually need this R and P to compute the best policy. Best policy is simply just like Q as a max, max is a kind of A, right? IS. So, actually, I didn't exactly follow the location of the paper I read. They use Q star as A to denote what I described there. Therefore, I have a little bit problem when I wrote down this. But anyway, so let's see how we can estimate this QSA here. So what do you think what we can do here? I should have did that. So again, like what we want to do is that we simply want to estimate this QSA here, right? Or Q star SA here, whatever. Without actually need to know this RS A and also this PS pi, this transition probability here. So what they did is very simple, right? So just think of Monte Carlo. We don't actually need to know this thing here, right? We can just estimate this directly if we run through the experiment in the sense that, like, let's say if I start with a state S here, and if I somehow do whatever action, I don't know what kind of action I did, let's say I do whatever action A here, if I turns out end up in S pi here, and of course I know I have some reward, right? I don't know this reward function exactly. Actually, you may learn this reward function. After a while, you should know this. I did it quickly. If this is not too big. But anyway, but you can get this reward function anyway. You should receive some kind of reward. That, let's say this is R here. You know this R here? That is equal to this R. Actually, you may not know this R, big matrix R exactly. This R function exactly, but you know instantaneously what R is. And also you know what state you transition into, right? You know S pi here, right? And then like, okay, therefore I can just approximate this Q as this R here plus this, if I transition, if I make to a state, let's see here. Okay, I need to deal with this V star here, of course. But what is V star? Let's say if I have an initial approximation of Q, not exactly initial approximation, you just randomly set up a Q here. Then this V star is basically should be Q S pi A, right? Kind of. At least this is the best approximate you can do it. So let's say you have a may not be a very good approximate of Q here, but if you have a pretty good approximate there, then your V star there should be just, okay, if you take an action A there, then your value should be just like Q S pi A there, right? So therefore, basically, you have an approximate of this Q here. So in the sense that I can write Q as A here as like kind of the reward I have plus, let's say, oh, I put plus here, plus this gamma S pi. Oh no, I don't have S pi here anymore. Plus gamma V S, I don't have V here also, Q S pi A, simply
A or A prime.
A.
You mean same action or you mean one action from the same set?
No, it's A because I think of like this example here. What is your V S here ultimately? It should be like oh okay, you're right. I should pick the maximum of that. That's because I should pick the one that is the best way. So okay, yeah, you're right. It shouldn't be A or A pi, but it should be the best one, right? Because I'm here, and then I know this QSA, at least estimate of QSA. So I should try, if I want to estimate the good QSA here, should be the one that kind of like, okay, I should need a VS here, and then VS should be the maximum over all this action here. Okay, this thing is always a bit confusing. Okay, so I should maximize A in AQ as pi A here. And remember, this is basically count B here. And usually like this, because now the what I want to say is you don't want to be too aggressive for this kind of update. You want to introduce some inertia always. So one way to introduce inertia is just to don't remove your previous information completely. So instead of updating like that, I can update like QSA, plus alpha, R plus gamma, max A, Q, S pi A, minus Q, S A. So this is like a learning way here. So you see that if I set the learning way equal to 1, then this thing basically cancels, it's just that. So if it's not equal to 1, it's less than, so alpha should be 0, 1, or of course it shouldn't be 0. So if it's kind of like less than 1, then you kind of remain some of this QSA here. Or actually a more intuitive way to write this would be like this, but people typically write it that way, right? This is more intuitive. Basically, like you take a piece of this, multiply by 1 minus alpha the other piece. So if your alpha is 1, then basically you only take this piece. If you decide less and less, you take more of them. So, and of course, you just do this intuitively, and then eventually you get hopefully you get a good estimate of this Q, then your best price is just estimate like this. This is the Q learning. I may mention a little bit trick for this one also. You see the one thing that's kind of troubling is that you're updating pretty slowly, because like for each instance, I say from S to S pi to so on, for each of these iteration steps, basically you have like big S so many states here. but you're only updating one entry of this QS here. So basically you have this matrix, it's like, this is like S big, and this is A here. But each time you walk by one step, you only are updating one value here. So a kind of common modification is instead of updating like this, I'll update every S here. So I have like this S instead of S. Maybe I call it okay. Let's use S hat. Let's say S hat is all S here, but I scale it by this ES hat here. So this ES hat is something called eligibility. Do they call it that way? Yeah, they call it eligibility. Something like. So basically, a scaling factor that like you okay, let me just write like what the scaling factor is like. The scaling factor can be like equal to ES hat is equal to sum over lambda gamma t minus k. K equal to CO to T, let's say, delta S, Sk. So this is just clinical delta function, this is delta S, Sk equal to 1 if Sk so otherwise. So what it did basically, so I take lambda is equal to lambda. Again, I set to 0 to 1 or something like that. So if lambda equal to 1, basically I just count how many times the state is visited. So then in the sense I'm still going to update even though the current state is not that state. But if it's like in the past if we visited this state pretty often, then I will still like try to use this to update that. And of course you can tune this lambda to kind of make the path is less important, like how fast the decay, like the path and so on. And for lambda equal to or lambda tends to 0, it basically get back to this update here, the original update we discussed there. And one more thing in terms of implementation is what action you should determine here, right? I didn't mention that what action you should do here. So, of course, apparently, if you have a very good estimation of QSA here, so this action should be just this one, right? I should just pick the action that maximize that QSA here, right? So, like, okay, I don't really like this. It's just basically should be just this one, right? But the problem, like right at the beginning, you didn't have like very accurate like QSA here. So what people call is like they have like fancy name for that. It's like exploration and exploitation. So exploration basically means that okay, I don't know at the beginning, I don't know what's my Q exactly. I just randomly, okay, they are very careful about it randomly because in practice if you really do it really randomly, actually you may the algorithm really sucks. So you want to do it a little bit wisely. For example, with our car example here, you may at least have some knowledge that you are here, you don't want to go out, like stuff like that. So you can kill some of this possible action. Like you can remove some of that from that side. And then exploitation, of course, is just you just take the maximum there. Okay, that's about all I have. Maybe just one tiny little trick here is like for computing this ES, actually we can compute more efficiently, not like this. Of course, this silly, you will never try to compute this like this. So instead, we can compute this like equal to gamma lambda ES plus 1 if S equal to current state. It's gamma lambda S plus. I hope it's not too difficult to see that this is equivalent of this. So like you basically, if you are not at this state, you basically you are kind of have this decay factor, where you just kind of scale by that decay factor. If you are the current state is actually equal to S, then besides this decay factor, you have this additional one, that contribution from the current state associated, which is add 1 there. And of course, typically this kind of actually, by the way, this thing, they have an algorithm called TD lambda. That idea is basically from this algorithm there, and of course with this trick you will come much faster, but you pay a little bit more overhead for each iteration. So I guess more or less that's all, but like I guess I probably generate many questions. I mean, the idea is quite simple, but I guess the notation is kind of confusing.
One question. The ES is the factor to keep the history of the QS. QS and A.
Is keep the history of
Previous actions.
whether a particular state, okay, ES hat will be keep a history, roughly speaking, like how often the state S hat is visited in a scale factor, in a normalized way. So if it's like, if you think it's like basically visited quite often, then we believe that like we should like update that state with a higher scale factor.
Okay, you mean if we have a lot of visits of the same state, we must
Not exactly. Yeah.
we
it's
must
okay.
increase the effect.
Yeah. I guess like I don't know whether they have mathematical proof for that. Yeah, they may. I don't know. Yeah. I guess intuitively it kind of makes sense, but sure, you can show that it's actually the optimum way for you to do that also, right? But if, you can search for TD lambda, and then you probably, the first paper probably will describe why they do that. Yeah. So, okay, I guess that's probably not totally accurate. I talk about it.